Assalamualaikum warahmatullahi wabarakatuh to my friends and fellow. Today we're going to learn about arms race model. Okay, before that, we need to know what is arms race. Okay, arms race occurs when two or more groups compete for military superiority. It consists of competition between two or more states to have superior armed force regarding weapons production, military growth, and superior military technological goals.
Let's take a closer look at the methodology we are using to model the expenditures incurred by two countries on armament. This is represented using a system of differential equations. Okay, we denote the expenditures of the two countries as x and y. The system of differential equations governing their interaction is given by dx over dt equal to ay minus bx plus r, and the other one dy over dt equals to bx minus qy plus s. Here a, b, p and q represent interaction coefficients that capture the dynamics between the two countries. Meanwhile, r and s are external inputs or influences such as economic resources or external pressures. And then to simplify the analysis, we rewrite the system in matrix form. X equal to ax plus b, where x equal to xy is the vector of expenditures, A is the coefficient matrix, and B represents external factors. The initial conditions are given by x0 equal to xy in a bracket. Now, let's consider an example. We assume the Richardson model parameters have the following values. From the values, we substitute this into the equations. We get A equals to -3, 2, 4, -1, B 2, 2, X 4, 1. This forms the system of differential equations that will guide our analysis. By formulating the problem this way, we can analyze the interplay between the two countries' expenditures more systematically and study the long-term behavior of their dynamics. Now, let's dive into the process of finding the eigenvalues and eigenvectors for the coefficient matrix A. This is a crucial step in understanding the dynamic of the system. To begin, we compute the characteristic equation. This is derived by solving the determinant equation using A minus lambda identity equals to 1. Substitute the matrix, and then we got -3, -lambda, 2, 4, -1, -4 equal to 0. And then we simplifying the determinant give us the quadratic equation. Lambda the power of 2 plus 4 lambda -5 equal to 0. And then we solve the quadratic equation using factorization. Thus the eigenvalues are, for the first lambda we got 1, and the second lambda we got -5. And then we find the eigenvectors corresponding to each eigenvalue. Starting with first lambda, -1, we substitute it into the matrix equation. A minus lambda I x equal to 0, and then we substitute, and then the eigenvector corresponding to first lambda equal to 1 is 1 and 1. This process can be repeated for a lambda second equal to -5 to find its eigenvector. Together, the eigenvalues and eigenvectors provide a complete picture of the system dynamics. In this slide, we will delve into solving a system of differential equations to model an arms race scenario using Richardson equations. Our goal is to find the specific solution by substituting the values of constants C1 and C2 into the general solutions. So the general solutions for the homogeneous system x equal to ax is given by xt equal to C1 1 e the power of t plus C2 2 -1 e the power of -5t. For the non-homogeneous system, x equal to ax plus b, we assume a solution of the form are e and f. By substituting this assumed solution into the system, we get the following equations: -3, 2, 4, 1. E and f plus 2 and 2 is equal to 0. Solving this equation allows us to determine the constants E and F, which describe the system's behavior over time. From this slide, we have successfully derived the solution that models the behavior of our system over time. This solution provides a comprehensive understanding of the system's dynamics, illustrating how the state variables xt and yt evolve over time. By solving this system, we gain insight into the stability and behavior of the arms race model we are analyzing.
Moving on to results and discussion. Based on our calculation just now, we will get two different type of equation. The first one is xt equals 4e to the power of t plus 8e to the power of negative 5t minus 2. And the second one is yt equals 4e to the power of t negative 4 minus 4e to the power of negative 5t minus 2. Okay, based on this equation, we can conclude that our problem is a runaway arms race because both equations show trends like exponential growth. Based on the graph, we can say that the equation xt represented by the green line start at much higher value and exhibit a noticeable downward trend or local minimum as the decay term 8e to the power of negative 5t weakens and the growth of the term 4e to the power of t begins to dominate. As t approaching to infinity, the equation grow exponentially caused by the e term. Okay, for equation of yt represented by the blue curve, it start at near negative region due to the negative term. As t approaching to infinity, the positive exponential term dominates, which cause the curve to grow steeply. Based on our calculation, we will get two different types of eigenvalues. The first one is lambda equals to 1 and the second one is lambda equals to negative 5. Let's see how these eigenvalues impact in real life situation. For the first one, for the positive eigenvalues, lambda equals to 1, it corresponds to a mode where the system grows exponentially with respect to time. This indicates that if one party try to increase their armaments level, the other might perceive it as a threat and increase their armaments too, which cause both party armaments level to grow exponentially. This can also mean that the escalating tension between parties where both try to outmatch each other will lead to a runaway growth in armaments level. Next, for negative eigenvalues, lambda equals to negative 5 correspond to a mode where the system decays exponentially with time. The decay arises because of the negative eigenvalues, which cause it to diminish exponentially or signifying stabilization. In real life situation, this could represent a temporary adjustment or describe initial attempts at stabilization caused by the exponential growth that comes from the positive eigenvalue as I said just now. After much discussion, we can translate that initially both modes influence the system, and there may be complex interaction where stabilization attempts temporarily counteract runaway growth. However, as t approaching to infinity, the term e to the power of negative 5t diminished to zero, which means that any stabilizing effect vanish in the long term. We can conclude that the outcome is ultimately dictated by the term e to the power of t, in which the levels of armaments of both parties rapidly increase, resulting in a runaway arms race.
Okay, so the conclusion that we can make from the Richardson model in example 7.22 that illustrate the dynamic of system linear differential equation, which the extraction stating entities produce different behavior that determined by the system eigenvalues, with one mode of the system rising exponentially and the other decreasing exponentially. So the saddle point behavior is indicated by the eigenvalues lambda 1 equal to 1, we get positive, and lambda 2 equal to negative 5, we get negative. So the presence of the exponential growth term e to the power of t driven by the positive eigenvalues that signifies a runaway arm race, where the system become increasingly unstable over time, while the exponential growth dominate, leading to escalation. This analysis shows the highlight the potential of instability and uncontrolled competition in scenarios modeled by the system. Okay, so lastly, Richardson race model demonstrate the unstable system due to the presence of positive eigenvalues, which drive exponential growth in armament expeditions. This lead to a runaway arm race where both countries escalate their expansion without bound. So the solution shows that while the initial condition and specific parameters influence the dynamic, the system instability is rooted in the metric A governing interaction. The behavior emphasized the critical role of mutual cooperation and control measures to avoid uncontrolled growth and maintain stability in such competitive interaction. So that's all. Thank you.